And question 6b, limestone is an ore of calcium that contains a high proportion of calcium carbonate. Calcium carbonate reacts with hydrochloric acid according to the equation that's stated there. A 1.75 gram sample of limestone is added to an excess of hydrochloric acid at a pressure of 101 kilopascals. 280 centimeters cubed of carbon dioxide gas is formed at a temperature of 22 degrees C. It was assumed that all the CO2 gas produced was formed during the reaction between the calcium carbonate and the HCl, and calculate therefore the percentage of calcium carbonate in the limestone sample. This is a tricky calculation. There's lots going on. You've got no structure of how to build this up, so you've got to put all that in yourself to lead you towards the correct answer. So clues in this question. We've been given pressures, we've got volumes, we've got temperatures. So this is all screaming at me. I need to use that relationship there. This is the ideal gas equation, and you need to use this for any calculations involving gases that aren't at room temperature and pressure. So if that's not stated in the question, if you're given volumes and temperatures, etc., and pressures, then you know you're going to need to use this expression. Now, dealing with the ideal gas equation is not really that difficult. The hardest bit, and the bit which students often forget to do, is convert the units into the ones that are needed to be used in this expression. So, if we remind ourselves of that, for the ideal gases expression, all pressures need to be in pascals. So we're going to need to convert this from kilopascals into pascals. Volumes all need to be in meters cubed. Unusual value is the SI unit for volume, but obviously in chemistry we tend to deal in centimeters cubed and decimeters cubed, but for the purpose of the ideal gas law we need volumes in meters cubed. And lastly, temperatures need to be in Kelvin. So we're going to have to convert all of these values into the correct units first to make sure we can deal with the ideal gas equation properly. So let's start with that. Okay, we have got 280 centimeters cubed as our volume. We need that in meters cubed. Okay, so what we need to know, meters cubed obviously is the biggest volume out of centimeters, decimeters, and etc. So we know there's 1,000 centimeters cubed in decimeters cubed, and there are 1,000 decimeters cubed in a meters cubed. Therefore, there are 1,000,000 centimeters cubed in a meters cubed. So 280 centimeters cubed is going to be the same as 0.28 decimeters cubed, times it by 1,000, times it by 1,000 again is going to give me 2.8 times 10 to the minus 4. Sorry, dividing by 1,000, not timesing by 1,000. We divide by 1,000 because meters cubed are the biggest one. So 280 centimeter cubed divided by 1,000 gives me the value in decimeters cubed. Divided by 1,000 again gives me it in meters cubed. So that's the volume value I'm going to need to use here. Temperature, 22 degrees C. We want it in Kelvin. Now, Kelvin is a linear scale. There's no negative numbers. 0 Kelvin is the lowest temperature you can get. And the useful relationship is that 1 degree C is the same quantity as 1 Kelvin. All right. The idea here, though, is that 0 degrees C is equal to 273 Kelvin. But then if you increase degree C by 1, you increase Kelvin by 1. So if 0 degrees C is 273 Kelvin, then 1 degree C is 274 Kelvin, and so on. So the increments are exactly the same. So if 0 degrees C equals 273 Kelvin, all we've got to do is add 22 to 273. So 22 degrees in Kelvin is 295. And then lastly, pascals, pressure. We've got pressure in kilopascals. There's 1,000 pascals in a kilopascal. So to convert this to pascals, I would need to times by 1,000, which means I've got 101,000 pascals. So these are the three quantities, the three correct units I'm going to need to use in the ideal gas equation. So let's go back to the question now, converted everything, and we can figure out what's going on. I've been given a 1.75 gram sample of limestone. We know limestone therefore contains calcium carbonate, so we can't assume that 1.75 grams is the mass of the calcium carbonate, because limestone contains other things as well. And that's, again, an assumption that students make with these sorts of questions, which then leads you down the wrong direction. So we can't assume that. We're going to have to work out how many moles of calcium carbonate we've actually got using the ideal gas law. We can't just do mass over molar mass, because this isn't the mass of the calcium carbonate. This is the mass of the limestone, which contains this amongst other things. So if I want to calculate the percentage of calcium carbonate in the limestone, I need to figure out, well, how much of my limestone was calcium carbonate? How many moles were there? And only the calcium carbonate will react with the HCl. All the other stuff that's there, the impurities, anything else that's in the rock, will not react with the acid. And that's the basis of these calculations, is that if we can figure out then how much of the CO2 is produced using the ideal gas law, we know that is related to the amount of calcium carbonate, and then we can figure out the mass via percentage. So I've got my values. I therefore need to figure out the number of moles of CO2 that were produced in this reaction. So let's start here. We know that PV equals nRT. I need to rearrange this so I have the number of moles. N is going to be equal to PV over RT. All right, it's N times RT. I want N on its own, so I divide both sides by RT. And actually, just doing that will get you a mark on the exam. It's showing you the exam and you've understood how to rearrange an equation. So N equals PV over RT. Let's now plug our numbers in. This is where we use the correct units in the calculation. P for pressure, 101,000. V for volume, 2.8 times 10 to the minus 4. Over R, this is the gas constant, and this value, 8.314, is on your data sheet. Let me bring that in to show you that it is there. Here is the OCR data sheet. On the first page, you see this general information section, and there's your Avogadro's constant, and there at the bottom, gas constant, 8.314 joules per mole per Kelvin. So that's the value you need to use for your R. So 8.314 times by temperature in Kelvin, 295. Okay, so you work that out. So multiply the top out, multiply the bottom out. Top divided by bottom will give you an answer of number of moles of 0.0115. Okay, that'll be another mark there. So it worked out, this is the number of moles, let's put it on this side, the moles of CO2, because we're dealing with the ideal gas equation. All right. Therefore, look at the reacting ratio. 1 mole of carbon dioxide is produced by 1 mole of calcium carbonate. So we can also say that this value, 0.115, is equal to the moles of CaCO3. All right, 1-to-1 ratio, so the moles of carbon dioxide is equal to the number of moles of calcium carbonate. So using that value now, I can work out the mass of calcium carbonate that was present in the sample, because mass is moles times by molar mass. We've worked out the moles, 0.0115. The molar mass of calcium carbonate, 40.1 plus 12 plus 3 16s at 48 is 100.1. That gives me then 1.115 grams. So this is where this value now comes into play. Remember, this mass, the 1.75, was the mass of the limestone. We have now worked out, using the reacting ratios, to use the proper term, the stoichiometry present in this equation, that there was this amount of calcium carbonate present in the limestone. And the question is asking to work out percentage present in the limestone. So your percentage of CaCO3 in the limestone, you take the mass of your calcium carbonate, 1.15115, and divide that by the mass of the sample, 1.75, and as its percentage, times that by 100. That gives me then an answer of 65.78%, and that is your final answer there. All right, so there's no information on rounding, so you could round that to 65.8, and that would be absolutely fine as well. There we go. So a tough calculation. There's lots going on in there. That's why it's worth 5 marks. So for any of the ideal gas equations, any calculations involving this, think about how you rearrange it. But the most important thing was that section there. You've got to make sure you convert your units.